Okay, so in this second lecture of chapter 15, we are going to talk about thermodynamic processes. The subject may sound a little abstract, but let me try to give you an idea of how useful it is. Okay? What we want, as we said, is to use heat, use this energy that is being transferred to get work done. And so we want to create a machine that will do some kind of work. And what we want to find out is what is the best way to get this work done? What is the most efficient way? And so we want to find out what is the best sequence of thermodynamic processes that will give us the most efficient machine, for example. That's more or less the idea, okay? Just to try to make this topic a little bit less abstract than it may sound. The first kind of thermodynamic process we'll discuss is what we call isothermal process. Iso means the same, equal, thermal, temperature. Now, so isothermal process is a process where the temperature never changes. The temperature is constant. And I'm going to write this here. So an isothermal process, the temperature is constant. It doesn't change. Okay, in order for an isothermal process to take place, we are going to assume that the system is in contact with a heat reservoir. So which system I'm going to consider? I'm going to consider something like this, okay, where I have a certain recipient with an ideal gas inside, and I have this piston which can be moved. So I can expand this gas, this gas can expand or I can contract. So this volume can change, okay? And what we are seeing here, for this process to be isothermal, what we need is to put this system in contact with an enormous heat reservoir. Why? Because this heat reservoir is so big that will make sure that the temperature of this system never changes. It may change its volume, its pressure, things may happen to it, but its temperature will never change. Okay, so we have here this enormous heat reservoir. Okay, and we have here our recipient with that piston. All right. Okay, so what are we going to do? What is the idea of this isothermal process? Heat is going to be added to this system. Now, heat from this reservoir. And this system is initially in this state where we have a certain volume, VA, and a certain pressure, PA. But as heat is being added, what is going to happen is that this piston, let me make it, will, from this point where it was initially, it will move, the gas will expand, and we are going to reach this other point where we are now going to have VB, a bigger volume, and a different pressure, PB, a smaller pressure. Okay? Throughout this process, the temperature is kept constant. Well, we are talking here about an ideal gas, so that means that the product PV is constant, right? Because we as we saw in chapter 13, we know that PV for an ideal gas is nRT. If the temperature is not changing, this PV, this product, is not changing. So I know that PAVA is equal to PBVB. All right? And I can make a plot of this pressure versus volume. Let's make a plot. For this isothermal process, if I make a plot of pressure versus volume, I would have something like this. I started at this pressure PA, and we had this volume VA. The piston expanded, no? the system expanded, so we ended up at this new volume VB at a different pressure PB. Throughout this line, any point of this line, the temperature is exactly the same because this is an isothermal process. So these kind of curves, they are called isotherms. So that's what you see here in the text. Okay. Now, if I give you a curve like this, but let me give you two curves, this one, and let me give you this other one here. Okay, so you have now these two curves. They are both isotherms. So suppose you have a problem like this where they say this is a plot of pressure versus volume. You have these two curves, the black one and the blue one. They are isotherms. So any point on the black has a certain temperature. Any point on the blue has another temperature, but any point here is the same temperature. And suppose they ask you, which one has a higher temperature, the black isotherm or the blue isotherm? What would you say? Think a little bit and then answer this question. Stop the video and try to answer this question. I'm going to answer you. The black one has higher temperature. The blue one has lower temperature. How do we know that? Well, let's pick a point. Let's pick, for example, this point here where the pressure is PA, okay? And let's go along this line. Well, here we said that we have VA. At this point for the blue line, I'll call this another V. I'll call it VA prime, okay? We know that PA, VA prime is a certain temperature. I'll call it T prime. We know that PA, VA, which is our black curve, has a certain temperature T. Okay, so this is our black isotherm, and this here is on our blue isotherm. Which one is bigger? Which one has the higher temperature? Well, the pressure, I picked the point where the pressure is the same, and you see that here is the point for the black. Here is the point for the blue. This point here has a higher volume. So we know then that the black one has a higher temperature. Okay, so just by looking at these two curves, picking a point there, you can determine which one has a higher temperature. There is one more important thing to talk about these isothermal processes. What we have here, well, let's discuss the scenario that we had here. Now we said that heat is being added and then the volume changes. Volume changes means work is being done. Now, volume, we have a displacement here, we have work being done. Work being done by the system. So if we go back to the first law of thermodynamics, what would we say? Well, delta U, the change in internal energy, is Q, the Q that is being added by this enormous reservoir, minus the work that is being done by the system. That's what we said is the equation for the first law. But for this specific thermodynamic process, we are saying the temperature is constant. Okay, if the temperature is constant, there is something here that is not changing in our equation for the first law. What is not changing? Delta U. Remember that we said delta U is associated with the change in temperature. Delta U is 3/2 of nR delta T. If the temperature is constant, this is 0. Okay, so what we conclude that in an isothermal process, in an isothermal process, all the heat that is being added to the system via the heat reservoir is used to get work done. So Q is equal to the work. Okay, so this is an equation valid for isothermal processes. These isothermal processes, they happen very slowly, okay? Because that's what guarantees that as the heat is being added and the work is being done, things that are happening gradually, so we don't get the chance to change the temperature, okay? So important topics: isothermal, constant temperature, Q is equal to the work because the temperature does not change, so there is no change in internal energy, and this kind of plots. Now, being able to identify which isotherm has a higher temperature. So this is the important topics for this first process, which is the isothermal process.